we now turn to experiment 2, which is pressure gauge testing. And we're going to get into the nitty-gritty of the pressure gauges and the pressure gauge tester for a minute, but I want to spend a few minutes talking about the basic theory behind this and about the basic theory of fluids in general. We're going to, I informally divide, I do a lot of things informally in this course, fluids into several types of applications. One of them, static applications, where the fluid is stationary. That fluid doesn't move. And there are many applications of fluid statics, brakes. There's a good example of a fluid statics, which is appropriate because it's supposed to stop something. Some hydraulic applications are static applications. Basically where the fluid is motionless. That's the pressure gauge testing is an example of fluid statics. And then we have state where the fluid is moving, but that movement is not varying in time. And that's a very loose way of putting it, because with turbulence, that really isn't so, but we try to make as much of the steady state problem as we can get away with. Your wind tunnel is going to be that kind of experiment. In fact, the wind tunnel is, the hydraulic jump is, the flow meters are, and that kind of thing. Those are dynamic, as opposed to the static, where this buoyancy and stability, and to some extent rotating drum, is more of a static type of application, although it's sort of between the two. And finally, last, and one which we won't see in this course, is dynamic unsteady state, where not only is fluid moving, but it's not doing so at a constant rate. And we see many problems like this, but we're not going to get that far in this lab. Okay, let's start with the statics. And let's define what a fluid. The fluid definition is something that can, in the formal definition, is something that continuously deforms under shear. Well, the problem with that definition from a conceptual standpoint is that if it deforms, it's moving. And so therefore it's kind of a self-defeating. As we're going to see, fluids that move do present shear stress. That's what the viscosity experiment is going to be all about. And that is a fluid, steady state dynamic type of experiment. But in the meanwhile, we've had most students who get fluid mechanics get hit by solid mechanics first. What's the difference? Most of you, I will explain in terms of a mechanics and materials approach to the problem. Most of you who have taken fluid mechanics, or solid mechanics of materials, whatever, have seen this, where you take a little element, cubic element, we're going to do it three-dimensionally. It has normal stresses and you can tell that I'm deeply rooted in geotech because I do compressive stresses first. But they also have shear stresses on all four of the surfaces. And if we talk about this is tau xy, and I'm going to use the old goat's notation for this. So just be tau yz and tau xy. In mechanics of materials, we talk about how to determine those and what effect they have on the structure, i.e. failure, deformation and failure. That's what mechanics of materials is all about. In a fluid, in a static fluid, the shear stresses go away. And once the shear stress goes away, the fluid is in a state called a hydrostatic. And in fact, we can, it's in a hydrostatic state. All three of these, which are now what we call more pressures commonly in fluid mechanics, are equal. And that is Pascal's law. Basically, if I have a confined area, and I have a pressure within, I pressurize this, fluid doesn't move, it's a confined area, the pressure is uniform in that area and is the same in all directions. That's important for several reasons. One of them, it's an illustration of hydrostatic stresses, and second of all, when we get to the actual testing machine, we will see that the fluid, what we will see is that the pressure gauges we're testing are pointed in different directions. Pascal's law basically says we can do that. In other words, we don't have to point them all in one direction, because in this static fluid static situation where this is enclosed and the pressure is uniform, all three gauges are going to be reading the same pressure as long as they're communicating in the system. That's important. There are no shear stresses. Going around corners isn't going to present problems at all. That's important from a number of standpoints, not the least of which is that in fluid power, it makes it easier to essentially send energy around corners. Now, there are losses associated with that. We're going to get to that too. But in fluids, when we have a situation where we need to essentially route power and energy in geometrically complicated ways, fluid power is a very convenient way to do it. And we see that. So therefore, that's how this works. If I, for example, apply a pressure, a force, at one point, which I'm going to, this is a dead weight pressure gauge tester, we apply a force using gravity to an area, which is right here, which the diameter of that little plunger to four, we apply a force to gravity, and that produces a pressure which is equal to force over area, and that pressure is communicated throughout the entire internal of the structure, or in this case, in terms of the fluid cavity. Excuse me, I've spent too much time in structures. The fluid cavity. The entire fluid cavity has one pressure, and those pressures can be read by one gauge, or in our case, at least to start with, 3 gauges. So therefore, that's the basic principle how this works, and that also explains the difference between a fluid and a solid. If you have a solid and you apply some force to it to induce stress in it, you will get somewhere along the way shear stresses. With a fluid, as long as the fluid is not moving, you will not, if it's a true fluid. Now, there are materials that kind of push the envelope in terms of being one or the other. And some of the fun of engineering is trying to learn about the subtle differences between those. But in any event, for normal fluid, for normal fluids, for true fluids, the shear stresses are gone statically, and we can do this. This is the Ashcroft pressure gauge tester. Yes, it's old. I think the record shows it dates from the early 1990s. But in any event, it is what it is, and that's what we're going to use to demonstrate Bourdon pressure gauge testing. But first, perhaps it would be useful if we took a look at what a Bourdon pressure gauge is. So I'm going to put one up in front of the camera here. You see that it is basically a not entirely circular tube. Basically what happens is that as the tube is pressurized, it flattens out. And as it's flattening out on one side, it's increasing the pressure on another. Now, this is obviously old and not particularly accurate, but it gives you an idea of what's going on with the Bourdon pressure gauge. As it flattens out, it increases the pressure. These have been used since Bourdon came up with these in the 19th century. This is the reservoir fork. This is where the oil is stored so that you can, and it actually uses an oil. This is a miniature hydraulic system. Basically, you have a reservoir, you have the pump, which we use to actually put pressurized oil into the system. The pump works when, or actually pressurize the system when this valve is closed. This is the relief valve, and when it's open, you can't pressurize, but when you close it, you do. We're basically pressurizing this fluid. We're doing work on these three Bourdon pressure gauges, and then when we're done, we release it, and it goes back to tank. So we basically put energy in the system, we do some work, and then we release it. Every hydraulic system out there operates on this basic principle. And, whether or not it has a prime mover of a diesel engine or electric motor or whatever, that's pretty much the way they all work. So this is a good lesson in that. And I've got a link to my site on a little more detail on that. Another thing I have a little link to my site on are all these. These are all all of this plumbing is put together with pipe taps. One of the things I have found out in teaching classes now as opposed to what we did back in the dinosaur age is that many, even mechanical engineers, don't have a familiarity with a lot of what I call dirty iron type of engineering. And yet, pipe taps are something we use every day, we have it in our house and whatnot, and it's something you should become familiar with. It goes back actually to the 19th century. And I have a history of that along with how they're size and dimensions and whatnot on another link from my website. So, with that out of the way, basically I'm going to do this work. I'm going to pressurize these three gauges. This gauge has a maximum pressure of 300 psi. This gauge has a maximum pressure of 600 psi, and this one has a maximum pressure of 1,000 psi. Now you ask, well, that shouldn't, and they're pressurized by this. This is the dead weight pressure gauge. What we're going to do is we're going to put weights on this thing, and we're going to actually take those weights and we're going to create a dead weight pressure, and then that's going to pressurize the system. And then we compare the dead weight, which is our reference, to the actual weight to the actual pressures we get out of the gauges. Now obviously the dead weight is the reference, and these are what it's reporting. Your question is, how accurate are they? You're about to find out. And I'm not really sure because I just had to replace this one because it broke one of the pipe fittings. So, in any event, but these are not new gauges by any stretch of the imagination. So, in any event, that's the basic thing we're going to do with the dead weight pressure gauge tester. And it probably would be good to pause and consider the dead weights themselves. These are the dead weights. This dead weight is very thin and is the smallest. If you put this on top of this, already had dead weight, and theoretically of 25 psi. To be honest, this machine doesn't do very well at very low pressures. So we're going to start at 100. But if you put this on here, 25 plus 25, you would get 50 psi. The next one is, in fact, itself 50 psi. So, and it's a little bigger, but it's still fairly thin. If I put this added to that, I would get 100 psi of pressure. And then, and of course, I'm not going to get anything until I actually start pumping this thing. This is the 100 psi gauge weight. I put this on top. I've got 25, 50, 100, plus 100 is 200 psi. And last but not least, and actually most, is the 200 gauge. I'm using the H correlation, by the way. You can put two different sizes of piston in this. If I put this on top, when it gets to the 200's already there, I'll have 400 psi. And I have more of these weights, and I'm going to mix and match these weights. So you need to, when you're actually looking at this, the video I'm about to do, or the series of photos I'm about to do of this, you need to note what's sitting on top of here, and to make sure that you understand what's sitting on top of there, because that determines what kind of pressure you can expect out of these gauges. Now you ask, 300 psi, 6,000. What happens when, for example, I get to 350? What's going to happen to this gauge? Well, the worst possible case, of course, is what we call a missile reaction, where the thing would come shooting out. The next worst possible reaction is it starts leaking, and the next possible reaction after that is the gauge breaks. So what we're going to do to prevent that is we have two needle valves. And these needle valves are currently in the open position, or they're about to be in the open position, let's put it that way. When I get to 300, I'm going to close this valve. And this is going to be isolated from the system. Then when I keep pumping up to 600, I'm going to close this valve, and this gauge will be isolated from the system, and I'm going to take it all the way up, or at least as far as it'll go, to 1,000 psi. I have the dead weights to do that. So let's go ahead, and I'm going to show you a series of still photos at each of the data points, which your procedure requires you to take records of. You're going to be able to see, this gauge is upside down, I know it, but in any event, you're going to be able to see, hopefully, the different readings of these gauges. And you're going to be able to record those, and you're going to be able to use to correlate those. So let's go ahead and get started. I'm currently at 200, and I'm going to show how to get from 200 to 250. I didn't want to use the very early steps, because to get the first 100 is very tricky. So let's just go with 200. To add another 50, what I'm going to do is I'm going to take off one of the 50s and add one of the 100s. Now you will notice that the piston drops to the bottom. And so therefore, what I want to do is I want to have this thing to float. I want this thing to be in static equilibrium between the weights on the top and the pressure at the bottom. So I'm going to go ahead and I'm going to start pumping. And I notice that the gauges increases. Oops, I've overdone it. See, now I'm at the top and it goes up. So what I have to do is to release it. And again, this is not the easiest thing to do. Now I want to check it. It's still kind of pegged at the top, so I'll release it just very slightly. There, I have it. That's 250. And we do that for each step all the way from 100 up to 1,000. Now I've reached 300. I will close this valve. And I'll simplify the weights just a little bit. I'm going to take these off. That would be 50. That would be 100. And that is 200 to make 300. So we're in the same basic weight we had before. Now we're going to proceed in increments of 100 on up to 1,000. Now we've reached 600. Keep in mind that my objective in this is to make sure that the weights float like this, that they're not bumping the top or the bottom. So with that out of the way, I'm going to go ahead and turn my 600 gauge off. And we're just going to proceed with that one on up to 1,000. Okay, that's it. When you're done, you open all these valves. You depressurize the entire system, and the entire system goes back to zero. And your task will be to take and as your x-axis, these pressures, the pressures that came from the dead weights. And then, on the other hand, you've got actually 3 different correlations to do. The correlation for the 300 psi gauge, the 600 psi gauge, and the 1,000 psi gauge. And once you've done those correlations, then you can and actually compare them. They should be ideally linear. I will stick with linear correlations for all of these. And so when you're done, you will be able to make some kind of determination of how accurate you think these gauges really are, not just from an eyeball standpoint, but from a statistical standpoint. You can apply Chauvin's criteria, you can apply student T, since this is a fairly small sample, for each of these gauges, and find out whether there are any outliers in the data as well. So, in any event, that's it for this experiment. Thank you for watching, and God bless.